All right, welcome back. So remember we were just looking at the situation where we had an exact couple, and I'm thinking of this bigraded example, so I'll write it as though it were that way. Though it's okay if it's singly graded or triply graded, really could be anything. And I'm indexing this like it's a cohomological spectral sequence we're going to get, but again, I'm kind of agnostic about that. Okay, so we were thinking about the example. We're doing this in full generality, but I find it helpful to carry an example along, so we're thinking about the example with, that's unreadable, though you probably know what it says. Okay, with E1 PQ just being our P plus Qth cohomology of XP relative to XP minus 1. Okay, and I don't want to remind you sort of all of the technical notation. Most of it was there so that we could write down our spectral sequence and say what the ER page was and so on. But for now, I'm going to say, yeah, we have our spectral sequence. We've checked all of that stuff. And we really just need to think about what we're converging to. So our E infinity terms and the thing we're trying to compute, which is probably these D's. Okay, so I have this diagram where I is whatever the map is between the D's. Here that's induced by the inclusion of the filtered pieces of our space, and we defined a bunch of things. So one was our D minus infinity comma star. So remember, I'm just keeping track of one of the gradings because that's really all I need, and just collecting up all the rest of the other grading. So this is just going to be the colimit of the diagram with these I maps. Then we had D infinity star. So that was the inverse limit. And whenever we take an inverse limit, we should think about the fact that inverse limit is not exact. And so let's think about the lim1 term as well. Okay, so that's just the derived inverse limit for that same thing. And in this example, we're thinking about the cohomology of a filtered space. Then this colimit, well, we're going to eventually get down to x minus 1. And remember, our cohomology of x minus 1 is just 0. So in our case, that one will be 0. And these other two really tell us a little bit about the cohomology of x, right? That fits into a short exact sequence. Okay, if we were talking about homology, then really it's this colimit that would tell us about the homology of x. So maybe off here in parentheses, and these other two would be about the homology of x minus 1, and of course they'd both be 0. Okay, so as we said at the end of the last video, often it's the case that one of these is 0. I guess I wrote this one first, so let's do that. Okay, so, well, all right, we set up a lot of the stuff to have the spectral sequence, but if these are the things that we want to be converging to, then really we need some filtrations of them, and then we need to identify those filtration quotients with our E infinity terms. So I'm not going to prove all of the pieces of that. Let me just say C. Boardman or McCleary. But I will tell you what the filtrations are. So how can we filter these things? Oh, I guess this is a way to go from an exact couple to a filtration, but somehow I don't recover all the kinds of filtrations I'm familiar with. But in any case, filter, well, okay, I'm writing these backwards. So let's filter the inverse limit. I don't want to swap them because then I'll probably get confused and write the wrong thing. How can we filter the inverse limit? In our case, that's really the thing that we're interested in, right? We think we should be converging to that, and we'll filter it by taking the kernel of the map from the inverse limit to each piece, right? There's, I can never remember whether it should be called a cone or a cocone, but there's a map from the inverse limit to each piece, and it's the universal thing that admits such a map, and so we can look at each one of those maps and take the kernel. Similarly, for the colimit, we can filter that by, well, I'll make the pth thing be, now I'm filtering the negative infinity guy. I find it really hard to remember which one I'm doing. Okay, and we'll filter that by the image. And now, okay, well, I've swapped my variance. If I were talking about the colimit, maybe it's a cocone, whatever it is, it's the opposite of the other one. The point is that there's a map from every piece to the colimit, so we'll just take the image of that. Notice these are both decreasing filtrations. And that's a good thing to check, sanity check. So I've got these decreasing filtrations. And also notice that the filtration of the limit, this first one, using the kernel, that agrees with our filtration when we had a filtered space X that had a finite filtration, right? In that case, we didn't have to worry so hard about convergence. We checked that, yes, we had the nice things in the E infinity page and so on. And we took a kernel of something that looks very familiar. So you should, or very similar to this, I should say. So if that's not familiar, you should go back and compare these two and see that matches up. But this is sort of, I would say, maybe not obvious, but an obvious or reasonable generalization of that. How about that? So, okay, we're extending to the case where maybe it's not a finite filtration. And then I want to give this lemma, which I won't state exactly as is in here, but let me say this sort of corresponds to lemma 5.4 in Boardman, and it's also called proposition 3.16 in McCleary. And I'm really mixing the two of their notations and terminology, so it's kind of a mix of the two. Okay, but what is the upshot of both of these statements? Well, the first thing is that if we look at the filtration of the colimit, and I will say one thing I appreciate about Boardman's paper is that he keeps reminding you which one's limit and colimit. So that's our d minus infinity star. So this is the thing that should be, say, the homology of some filtered space, or 0 if we're doing cohomology. Okay, so the filtration by, well, what did we just filter it by? We said fp d minus infinity star, the pth piece, is just the image of the map to the colimit for each piece. Okay, again, I could have copied and pasted. One day I'm going to learn that lesson. In any case, okay, we already know that we have such a filtration, and I'm not going to do the thing where I identify it with the E infinity terms, but that is something that you might want to work through. But what I want to say about this filtration is that it's exhaustive. Okay, and that's one of those nice things that we would want for convergence, right? But it's not necessarily complete or Hausdorff. Okay, so it's not like we're always going to get strong convergence. That would be too much to hope for. But at least we can't mess up the exhaustive thing. Okay, so that's a nice thing about taking the exact couple. Now, the other statement I want to make here is about the filtration of the other thing, the inverse limit. So what can we say there? The filtration of the inverse limit, which we denoted d infinity star. And now maybe I will this time copy and paste. So it won't fit, okay. So we filter by this and by the kernel of these maps from the inverse limit. Well, the claim is that this is good in the other ways. So this is Hausdorff and complete. But not necessarily exhaustive. Okay, maybe let me say not necessarily exhaustive. And maybe some good exercises, by the way, is to come up with examples of how these things might break. But let me say it is exhaustive if we look at that colimit and it's 0. Okay, so that's really what we're going to want to use here, right? Is that this filtration, in that case, will be exhaustive, Hausdorff, and complete. That's all the stuff that we need for strong convergence. Well, strong convergence to the inverse limit. Okay, let's keep going on. So actually, I guess maybe it's worth pausing and emphasizing that right now. So what did we need to have a spectral sequence that converges strongly? We needed a filtration of the things that we identify the filtration quotients with the E infinity page, and that filtration had to be exhaustive, Hausdorff, and complete. So once we do that identification with the E infinity page of seeing that the filtration quotients here are E infinity terms that agree with what we said from our exact couple, then indeed we get strong convergence to this inverse limit. So that's nice. Okay, well, that depends on some things about identifying the E infinity pages and E infinity terms. And then remember that if we don't have finitely many things, we could run into some trouble. So let me continue on here. So Boardman defines a half-plane spectral sequence. Okay, well, you can imagine what that looks like. We just have non-zero terms in only half the plane, but this is going to be with exiting differentials. Okay, and that's a long term, but okay, a half-plane spectral sequence with exiting differentials. This, what does that mean? This says that for any PQ we look at, and it doesn't have to agree with our grading, but in some grading, so that this thing looks like it sits in a half plane, all but finitely many differentials I can't write this word. All but finitely many differentials exit the half plane, really the occupied half plane, and so vanish. Okay, so this is really just a way to get differentials going out to vanish. And this is almost the same, it's at least related to Weibel's terminology, where he described a spectral sequence as bounded below, as we saw. We said in particular half-plane spectral sequences of the right type were bounded below. And remember the term regular said that all but finitely many non-zero differentials out of at each spot are zero. Oh, sorry, all but finitely many differentials out of each spot are non-zero. No, I think I still said it backwards. It's getting late. Okay, I know this thing always says 9:41 a.m., but it's not. What am I trying to say? There are all but finitely many of the differentials going out at each spot are zero. There we go. Whew. Okay. In any case, the point is that in all of the stuff that we've been talking about, Boardman's version of convergence, up until now, we haven't had any of this kind of bounded below or regular or anything like that. So this is where that finally comes into play. Okay, and then Boardman has this theorem. It's sort of, I'm going to adjust it a little bit, but basically this theorem appears in Boardman. It's roughly 6.1. Says, suppose that you have an exact couple. Okay, and I'll use all the notation we've been using so far. And suppose this exact couple satisfies that you look at E1PQ, and this is 0 for all P greater than S. Okay, really the main difference here is that Boardman has for P greater than 0, but of course you could just re-index things and then you get P greater than S. So I'm just saying it doesn't have to fit squarely in a particular half plane. It could be, it could just have a sort of line of vanishing or something like that, an edge of the plane that vanishes. Okay, let me stop rambling. So what am I trying to say? Suppose the exact couple satisfies E1PQ is 0 for all P greater than S. And so yields a half-plane spectral sequence with exiting differentials. Okay, so again, I'm just not being so strict about what I mean by half. It's perfectly fine. Differences, differentials. Okay, there are going to be two versions. So if we look at d infinity star, remember that one is our inverse limit. If this is 0, then the spectral sequence converges. And even better, it converges strongly to the colimit. Okay, so that's what I mean about identifying these as the things that we're converging to. And when I say it converges strongly to the colimit, I also mean that those E infinity terms are the filtration quotients. So I won't write that, but it's implied here. And alternatively, if we know that the colimit is 0, well, then we have this half-plane spectral sequence, and the spectral sequence converges strongly again to the limit. Okay, and that's d infinity star. Okay, so for example, our homology spectral sequence has a good kind of convergence, right? Because there we have that that the inverse limit is 0, and so part A is going to give us nice, strong convergence to the colimit. On the other hand, if we think about cohomology, well, sure, we had that this colimit was 0, it converges strongly to the limit, but that limit is not necessarily exactly the thing that we were after, right? I should have said that's the inverse limit, right? Okay, so, and this is basically analogous to that previous version where we had our spectral sequence converges to the thing versus the completion of the thing. We can't tell the difference. This is telling us, yes, you should converge to the inverse limit. That's not necessarily the cohomology of your space. Okay, so it doesn't tell us about... Oh, sorry. And I also should have said we would like that to be true. It's certainly true if we're looking at some finite thing, then we don't even really have to worry about the limit. But our cohomology case, we're not going to have the E1PQ is 0 necessarily for all p greater than s. That seems quite unlikely if we have an infinite filtration. So, sorry, it's when we do homology, we'll have to come back and do this carefully, but when we do homology, then really we would want this to be like E1 minus P minus Q, and then we get that vanishing to the left, and that's what's going to do it. Okay. Let me try not to say any more false things at this particular moment. So for a half-plane spectral sequence with exiting differentials, then things are pretty nice. We get these two converges strongly statements. Okay, when we have a half-plane spectral sequence with entering differentials, which you can imagine is defined quite similarly, well, then things are a little bit more complicated. And even worse, if we have a whole plane spectral sequence, so then things get a lot more complicated. And this will come up especially when we're looking at, unbounded complexes, or we're working in spectra. This is definitely an issue that comes up. I'm going to only scratch the surface of this and say that if you are dealing with these kinds of spectral sequences, let's just leave that. If you're dealing with these kinds of spectral sequences, then yes, you need to be careful about convergence, and you should investigate carefully. Okay, I will go into a little bit more detail. So one of the things that we'll want to look at is Boardman's version of conditional convergence. So the spectral sequence for an exact couple, he says converges conditionally. And now, if you weren't confused about all the different kinds of convergence yet, maybe we've gotten you there. Okay, so now we have converges conditionally. Well, there's two versions. So it converges conditionally to the colimit. That's our d minus infinity. If d infinity, the limit, the inverse limit, is 0, and also its right derived term, right? It's lim 1. Okay, so that seems like a nice situation. Or we also say it converges conditionally, but then, okay, maybe here we say converges conditionally to the colimit, or we could say converges conditionally to the limit. And again, it's just sort of a little bit, maybe let's say inverse limit. Really, you're just after converging to one of these things probably in your spectral sequence, but we're kind of doing the homology and cohomology cases all at once here and dealing with the most general situation. So that's our inverse limit. We say it converges conditionally to the inverse limit if the colimit vanishes. Okay, well, fine, we can define that, but what does that do for us? Well, this is actually weaker than weak convergence. So this is like our weakest convergence yet. Okay, but in good cases, a lot of the time, you have more information. So maybe let me say in good cases, you can have some hypotheses. That imply strong convergence from conditional convergence. So it's not always true, and that's why it's weaker than weak convergence. It's not even always true that it implies weak convergence, but in good cases, there's vanishing of something, or you compute some term and you see, okay, yes, then we do have strong convergence. Okay, so this is a useful idea, and let's even make that precise. In particular, Boardman has this theorem that if we suppose our exact couple satisfies, and now this is going to be the dual hypothesis, so this is the one that we want for our cohomology. We'll say that E1PQ is 0 for P less than S, in our case less than or equal, or less than 0, I suppose, our S is 0. So if we're in this situation where we have this, and that tells us we have a half-plane spectral sequence, so we also want the half-plane spectral sequence that we get if this converges conditionally. And now I'm being vague here, but I mean to the limit, let's say to the colimit, or the limit, the inverse limit. Okay, so in either case, maybe let's just end the sentence there. Okay, what is the theorem? It says, in this situation, if you compute that right-derived E infinity term. Now, remember way back, we had we've been talking about the right-derived inverse limit, the lim1 term for our D infinity. That's a separate issue. But when we started writing down our E infinity terms, we had this right-derived of the E infinity. That's in the case where we don't know that those differentials settle down, right? And so really we have Z infinity mod B infinity, and Z infinity is defined by an inverse limit, and so it comes with a lim1 term. All right, and this is the right-derived functor of that. So if this vanishes everywhere, maybe I should put a star here. Then, oh, sorry, I didn't write vanishes. If this is 0, then the spectral sequence converges strongly. Okay, so that's a pretty neat thing. It's really saying this. It's our E infinity term is our obstruction to strong convergence, right? And so we can hopefully compute that thing, and if we can show that that vanishes, then conditional convergence can give us strong convergence. Okay, so this is really just an example of how you might use this, but maybe how would we want to use it? Well, if, for example, your spectral sequence is regular, and remember that said that I struggled so hard to say this earlier, that we have finitely many, see, I did that all but finitely many thing. That always, the too many double negatives. Okay, finitely many non-zero differentials should have looked ahead in my notes. Finitely many non-zero differentials out of each spot if these, if we have that situation where we're regular, so we have finitely many non-zero differentials going out of each PQ spot, then this RE infinity term vanishes. And now if we had a half-plane spectral sequence with conditional convergence, either to the limit or the co-limit, we would get strong convergence. Okay, so this is really how regularity is coming into play in Boardman's version. Though I think Boardman's conditional convergence is more general, and he investigates other possible ways for RE infinity to vanish. But the upshot is this RE infinity is an obstruction to the strong convergence, and this already shows up in a half-plane spectral sequence. When you have a whole plane spectral sequence, there's yet another obstruction. Boardman calls it W. I'm not going to deal with any whole plane spectral sequences for the moment, so let me just say I'll leave that for you to read on your own. But let me finish here with one last theorem, kind of tying this together. So suppose we have dp star equals 0 for all p less than 0. So we look at E1 PQ, and this is going to be 0 for all p less than 0. I have less than or equals written here, and I am not going to be able to figure out on the fly which one is correct, so let me just copy that down, but that should be a strict inequality. I think that's okay, but yeah, let me not think about it right now. Okay, so I want the dp star vanishes. That's going to tell me the E1 p star vanishes, and also, what's that going to tell me about the colimit? Well, that's going to vanish as well. Okay, well, then I've got a half-plane spectral sequence. So for the half-plane spectral sequence, this will be with entering differentials, which is not our best case. Glad this is almost the end of this video. I'm clearly struggling to function now. Okay, so for the half-plane spectral sequence with entering differentials, the claim is that R E infinity, the subtraction to our convergence, is 0 if and only if we look at that lim1 term for the thing that we're for our limit, and if that's 0, the RE infinity vanishes if and only if that's 0 and the spectral sequence converges strongly to the limit. Okay, so really this is going to be the situation that we're in for cohomology, right? If we're looking at the cohomology of a filtered space, we see that the half-plane spectral sequence with entering differentials, well, it won't always converge strongly, so there could be this obstruction, this RE infinity term. But really that's going to show up when we have this lim1 term showing up for our cohomology. So that kind of wraps up the story. All right, in the next video, and I think the last video that I'll do for convergence, this has been a long story, we'll actually look at the examples that we've been studying.